A quick question. When was the last time all major space agencies on Earth fell silent about the same cosmic event? I will wait. The answer is never. Not to that extent. In 2017, Oumuamua triggered a real flood of data, scientific articles, and press releases, and two I-borrows in 2019. The same thing. But 3I Atlas, our third confirmed interstellar visitor. We have fragments, hints, and many cautious evasive statements. Maybe it's just cosmic bad luck, timing issues, boring explanations, or perhaps silence is the only rational response when you've seen something you're not ready to announce. Stay until the end, for we will count how many days of prolonged silence it takes before we are forced to draw obvious conclusions. If this riddle has caught your attention as it did mine, don't forget to like and subscribe to not miss any updates as it unfolds in real time. Leave a comment about where you are listening from, what time it is for you, and whether you believe we are getting the full truth about the 3I Atlas. And if you want to help our community grow, share this video on social media or just in your group chats. You are the reason we can continue pursuing such stories. Thank you for supporting us. The void speaks louder. Imagine a solitary, vague point on the screen. That's all we have. The European Space Agency managed to capture her as she passed by Mars, a faint dot against the backdrop of space, barely distinguishable from the noise of the universe. This is the third known interstellar visitor to our solar system, captured from about 29 million kilometers away from the red planet. Honestly, it's not that impressive. Blurriness, whispers of light. But this is what makes you shudder. This blurriness persisted for 96 hours, possibly longer, under a veil of almost complete silence from the world's most powerful space agencies. Consider how quickly information usually spreads in our hyper-connected world. When an asteroid passes close to Earth, we receive press releases within hours. When a supernova flares in a distant galaxy, astronomers are already tweeting about it before the light completes its journey through our atmosphere. The machine of modern space science operates on immediacy, on the exchange of information, on the thrill of discovery broadcasted to anyone with internet access. So why, when an object from another star system passes through our neighborhood, do we receive nothing? NASA was remarkably silent, except for their early announcements. China's space program? Silence. The United Arab Emirates with their Hope probe on Mars. No word on observation attempts. It seems as if someone pressed the cosmic mute button just when we should have been hearing the most noise. You might think it's just a bureaucratic delay. Agencies need time to verify data, conduct calculations, and ensure they are not embarrassed by false statements. This is reasonable. This is how science works. But here's the thing. We have already had interstellar visitors. When Oumuamua flew by in 2017, the scientific community erupted with activity. Articles were published, data exchanged, telescopes around the world tried to catch at least one glimpse of it before it disappeared into the darkness. When two eyebrows appeared in 2019, spectral analyses, composition evaluations, and orbital predictions appeared on news sites within days. The system worked as expected, but now the feeling is completely different. This time, silence itself became a character in our story, a presence as tangible as the object we are trying to understand. When absence becomes the loudest signal in the room, one must ask what this absence is trying to tell us. Is it caution? Is it confusion? Or something completely different? Something that makes agencies choose their words so carefully that they would prefer to say nothing at all? Let me explain something important. The 3I Atlas is not our first interstellar visitor, but it may be the most significant. The stakes have changed since Oumuamua appeared. Back then we were children, seeing something magical for the first time, trying to understand what it meant. Now we have grown up, perhaps becoming more cautious. We had time to think about what it means when objects from other star systems can reach us. What possibilities does this open up? What questions does it make us ask? And perhaps that is why the silence feels heavier this time. Perhaps we are not sure we want to know the answers. Very soon we will explore the image from the European Space Agency, pixel by pixel, and find out why it should not exist under normal expectations. We will ask why spacecraft intended for studying Mars choose to direct their instruments at a dim object millions of kilometers away from us. But before we get there, I want you to ponder this discomfort a bit. If the silence continues, if no new data appears, if agencies keep offering only rehashed statements and old observations, we will default to the worst-case scenario. Not because we want it, not because it is the most likely explanation, but because the human mind craves to fill the void, and we will fill the silence with conjectures, even if we do not want to. In the history of space science, there is a certain pattern. Sometimes a delay gives rise to rumors. In the year 2011, when the Lennon comet was approaching, observations and official statements did not coincide in time. During this period, the internet spawned wild theories. They said she would cause earthquakes, that a spacecraft was watching her, that she would somehow pull the Earth out of its orbit. Of course, none of this was true. The comet broke apart before it reached perihelion. But the silence before this, the temporary void of information, allowed speculations to grow like bacteria in a warm environment. The lesson here is, when scientists do not speak, someone else will speak for them. Before assuming a conspiracy and letting our imagination run wild, we should examine the evidence we have more closely. We need to consider this blurry spot to understand what it may or may not tell us. If we are going to talk about silence, we must first understand what was spoken, even if in a quiet whisper, in this single captured image. Now let's move on to the second part, the image of the European Space Agency, which should not have existed. Let's talk about the European Space Agency's Martian orbital stations. The ExoMars Trace Gas Orbiter and Mars Express are not meant to be space paparazzi. These spacecraft exist for one purpose, to study Mars. The Trace Gas Orbiter analyzes the Martian atmosphere, investigating the presence of methane and other gases that may hint at geological or biological activity beneath the surface. Mars Express creates maps of the planet's surface, tracks its weather, and uses radar to penetrate the soil. These specialized tools are designed for a specific task, as if you sent a portrait photographer to capture geological formations. They excel at their work, but their task is very specialized. When the European Space Agency announced that they had received an image of Comet 3I Atlas during its closest approach to Mars on October 3, 2025, at a distance of about 29 million kilometers, the first question should be, how? These spacecraft were not designed to track extremely faint objects moving through deep space. Their cameras are optimized for planetary observations to capture the rusty surface of Mars in clear detail, rather than for detecting faint photons reflecting off distant objects. This is like using a microscope to observe the moon. Of course, you can see something, but it's not what this tool was designed for. What they managed to capture was, to put it mildly, unimpressive. A blurry, indistinct object without a clear cometary coma, that glowing, cloud-like envelope of gas and dust that usually surrounds a comet's nucleus. There was no clear tail extending from the sun, nor any distinct core, that solid heart of ice and stones we would expect to see. Just a blur, just noise, barely noticeable. Even skeptical scientists describe this observation as complex and barely discernible. One researcher noted that this was at the limit of the resolution capabilities of these instruments. Another said it resembled a very faint comet, but with significant uncertainty. For the comet that is supposed to be 3 and Atlas, we expect certain characteristics. Comets are dirty snowballs, frozen remnants formed during the creation of solar systems. As they approach a star, the ice sublimates, turning from solid to gas, bypassing the liquid state, creating a characteristic coma and tail. We must see streams of dust, asymmetric characteristics, and perhaps even distinct structures where the vents on the core eject material into space. We have observed this many times with comets in our solar system. It is predictable. It is understandable. So why does the 3I Atlas look like someone smeared a charcoal pencil on the sensor? The verified explanations are simple. It is extremely dim and located at a vast distance. The exposure time may have been insufficient. Motion blur is a real problem when trying to photograph something moving at tens of thousands of kilometers per hour. Overlaying multiple images to enhance the signal-to-noise ratio can introduce artifacts, create false details, or smooth out the real ones. All of this is quite likely and falls within the bounds of normal observational astronomy. We test these tools at the limits of their capabilities, and sometimes at these boundaries, pure data cannot be obtained. Instead, we encounter ambiguity. But let's approach the edge of this ambiguity and look beyond it. What if uncertainty is not a limitation of our tools? What if it is a feature, not a mistake? Think of a signal masked by noise. If you wanted to hide something in plain sight, making it unremarkable is quite effective. A clear shape, geometric pattern, obvious structure that would attract attention. But a blurred spot? That's easy to dismiss. This is exactly what we expect from the dim, distant comet, barely detectable. It fits our expectations so perfectly that we don't even think to ask questions. I'm not claiming that 3 Atlas intentionally hides something. I am saying that the data is ambiguous enough to conceal something, and we will not know it. Perhaps within this blur, there are structural features that we cannot resolve with current images. Perhaps the blurriness is artificially created, a cloud of reflective particles surrounding what we are yet to see. Or maybe it is exactly what it seems. A comet, so distant and dim that we are lucky to see anything at all. The problem is that, based solely on this image, we cannot make a distinction. Scientists hate ambiguity. They need clear data, distinct signals, results that confidently point in one direction. When the data is in this murky interim, capable of supporting multiple interpretations, instincts suggest to wait. Gather more observations, conduct additional models, double-check everything before making any claims, and perhaps this is part of the silence. Perhaps NASA and other agencies have data as ambiguous as this ESA image and are trying to understand what it means before saying anything publicly. Because as soon as you say something, as soon as you present an interpretation to the world, you cannot take it back. But here is what worries me. Even ambiguous data usually sparks discussions. Scientists argue about interpretations. They publish competing articles, engage in debates in conference halls and on social media. The process is dirty, but it is visible. Even this messy process seems muted with 3 AI's Atlas. It's not that no one is talking, but that the sound is muted, as if everyone is whispering, afraid of being overheard. In the next part, we will look at what NASA might know but isn't saying, or what they might be hiding. We will examine the data they released, the data they hinted at, and the noticeable gaps between them. Since this image from the European Space Agency raises doubts, NASA may have data that tells much more. The question is whether they will share this information. Part 3. The Quiet Corridors of NASA. NASA was not completely silent, let's be honest. They published some materials, including an animation on the multimedia page of Comet C 2019 Q4, Atlas, showing the object's trajectory through the solar system and its hyperbolic orbit, clearly indicating that it is not gravitationally bound to our sun. Images from the Hubble telescope taken on July 21, 2025, show a shape described as a dust cocoon, a roughly spherical cloud of particles surrounding the comet's nucleus. They issued official statements assuring us that the Earth is not in danger, that the orbit was precisely calculated, and that Tri-Eye Atlas would pass by and leave our system without incident. They even responded to speculation about extraterrestrial life, with a NASA representative stating that we are following the evidence, which currently points to a natural object. This is standard practice, as space agencies inform the public, provide assurances, and present data in accessible formats. But this is where it gets interesting. Look at the timelines. Hubble's observations were made on July 21st. When were they published? Check the press release dates, count how many days passed between the observation and publication. Now compare this with the typical publication timelines of Hubble data, considering the unusual nature of this object, the third confirmed interstellar visitor ever discovered. Do the timeframes align, or do they seem stretched, as if someone added buffer time? A pause, a moment for reflection before speaking. Then follows the incident with the Perseverance rover. On October 4, 2025, Avi Loeb, an astronomer from Harvard who became somewhat of a celebrity for his willingness to consider exotic hypotheses, published an analysis of what he called an image from the Perseverance navigation camera, which showed a stripe, a long elongated structure captured by the navigation camera of the Mars rover, which Loeb interpreted as a possible 3-eye atlas. The geometry was complex. The rover was on Mars, while Tri-Eye Atlas was tens of millions of kilometers away, making it unlikely to catch a faint object through Mars' dusty atmosphere with a navigation camera. Skeptics immediately raised objections, claiming that combining multiple frames to enhance the signal could lead to elongated artifacts, especially if the camera was moving or if the object was moving relative to the frame. The duration of exposure is important. If it is too short, not enough photons are gathered, and if it is too long, motion blur turns a point source into a line. The limitations do not coincide. Either the exposure was too short to capture something so faint, or it was long enough for the object to appear as a line rather than a band with sharper edges. The debates quickly became technical, delving into signal processing, photon counting, and the specific capabilities of navigation cameras. NASA never officially confirmed or denied Loeb's interpretation, They did not publish the raw data for independent analysis and did not make a statement that they studied the data. And here is what we think. They simply did not engage in discussion. This is strange. When a prominent scientist makes a claim about NASA data, even if it is controversial, agents usually respond. They might say they are verifying information or that their analysis differs, or even that they lack sufficient data for comments. Silence is not a typical response, so let's try to figure out what might be happening in the corridors of NASA. Perhaps they are verifying data from several sources. Space science requires a rigorous approach, and no one wants to announce something significant, only to retract it later when more accurate analysis emerges. There may be disagreements about how strongly to present any speculative interpretations. Bureaucracies are not monolithic. Different scholars, departments, and administrators have different opinions, and reaching a consensus can take time. Perhaps the information is deliberately being withheld until a consensus is reached, until everyone agrees on what can and cannot be said publicly. Or perhaps here we delve into more complex questions. They saw something uncomfortable or sensational and are waiting for confirmation before making a statement. Consider the consequences of announcing something truly anomalous. If NASA announced that it had found signs incompatible with the natural behavior of comets, the reaction would be immediate and intense. The media would explode, social networks would ignite, every conspiracy theorist would claim their correctness, and if it turned out to be a mistake, if further analysis showed it was just an artifact or misinterpretation, the damage to NASA's reputation would be significant. The structure of incentives leans towards caution, waiting until you are absolutely sure before making bold statements. But caution can appear as concealment, especially when the public craves information. The boundary between responsible science and strategic silence is thin, and from the outside, we cannot always understand which side of this boundary we are on. We can observe that NASA's communication style this time is different, more measured, more modest, more carefully controlled. Whether due to scientific uncertainty or something else, we simply do not know, and this uncertainty will deepen as our perspective expands. Because NASA is not the only player in this cosmic drama. In the next part, we will look behind the scenes globally and see that silence is not only the domain of NASA, it is a scheme that spans national borders, space agencies, and the entire apparatus of modern astronomy. When silence becomes the norm, covering continents and institutions, the question arises: is it connected to something common that everyone knows, but no one wants to talk about? The fourth part is a global veil. Space is not an American monopoly. Let's establish that right away. The universe belongs to everyone, and many countries are capable of observing, tracking, and studying objects like the three-eyed atlas. The Chinese National Space Administration manages a complex network of ground telescopes and space objects. The United Arab Emirates hopes that their Mars orbiter continues to return stunning data about the Martian atmosphere since its arrival in 2021. The European Space Agency, besides its Martian orbiter, has access to ground objects across the continent. The Russian Space Agency, Roscosmos, despite its reduced capabilities since the collapse of the Soviet Union, still retains observational abilities. The Indian Space Research Organization is making progress in observing deep space. This is a global endeavor, and when something significant happens, like the passage of an interstellar object, global participation is expected. Instead, we observe a choral silence. China made no press releases about the observations of the three-eyed atlas. The United Arab Emirates did not announce any attempts to recalibrate their instruments on this object. The USA published one blurry image, which we discussed, and then fell silent. Roscosmos is focused on its difficulties with the space station. Israel has made no public comments. It seems that everyone has simultaneously decided that this is not worth discussing, which is completely illogical considering the scientific value of studying an interstellar object. Let's consider the possible reasons for this collective silence. Firstly, technical limitations. Not every spacecraft or telescope is positioned or equipped to observe a dim, rapidly moving object millions of kilometers away. The UAE Mars orbital spacecraft is optimized for atmospheric studies of Mars, not for tracking deep space objects. Perhaps the Chinese space telescopes lacked a clear line of sight during critical observation moments. Roscosmos may simply lack the resources or means for significant participation. All of this is quite legitimate technical limitations. Secondly, internal political restrictions or confidentiality norms. Some countries treat their space program activities with great secrecy. For example, China is not known for quickly publishing scientific data for the global public. Information flows through official channels according to established deadlines, dictated not only by scientific curiosity. If Chinese telescopes detect something interesting, we may not hear about it for months or even years. It's simply the nature of their system. Thirdly, and here we move into a more speculative area, it could be coordinated silence, an embargo among agencies, official or unofficial, where everyone agrees to refrain from discussions until certain conditions are met. Perhaps this continues until the data reaches a threshold of reliability. Maybe they are waiting for approval from a leading agency like NASA, or until diplomatic or security considerations are taken into account. Space agencies indeed coordinate their actions, especially in large projects or discoveries. They exchange data based on agreements that sometimes include conditions about the timing of information publication. However, precedents in this matter cause confusion. When Oumuamua raced through our solar system in 2017, we witnessed active international cooperation. Data was freely exchanged between agencies. Scientific articles were published quickly. Various telescopes and countries contributed their parts to the overall picture. In 2019, when two Iberos appeared, the scenario repeated. Information was exchanged quickly. Press releases were coordinated but did not interfere with each other. The scientific community acted openly, as it should in science. However, with the emergence of 3I Atlas, this openness diminished. External observation of coordination has decreased, with fewer joint announcements and instances where agencies reference each other's observations. It appears more isolated and closed off. Each agency seems to operate in its own bubble, and these bubbles no longer connect as they once did. Whether this is an intentional decision or simply a consequence of time and circumstances, a sense of fragmentation is created, a system that no longer functions as it once did. Some media outlets noticed these gaps. Articles emerged questioning why China had not announced plans to study the 3I Atlas with its extensive network of telescopes. Others wondered why the UAE, having a perfectly positioned orbital spacecraft on Mars, had not attempted to conduct observations. The questions are valid, but answers do not come. Official channels remain largely silent on these issues. Here is a speculative scenario. Perhaps there is an implied agreement that one should not speak until NASA speaks. NASA remains the most prominent space agency in the world, with the largest budget, the most assets, and perhaps the greatest reputation. If NASA is cautious in how they articulate their observations of 3I Atlas, other agencies may follow their example, not because they receive orders, but because they sense the atmosphere. They see NASA's measured approach and think, maybe we should be cautious too. Perhaps it's worth waiting to see how everything unfolds before speaking up. But this creates a vicious cycle. If everyone waits for someone else to speak first, no one speaks. If everyone is cautious because everyone else is cautious, this cautious behavior becomes self-reinforcing. Silence continues not due to conspiracy or coordinated suppression, but due to a collective choice to avoid bold statements. It looks like a group of people standing at the edge of a cold pool, each waiting for someone else to jump in first. Is cosmic secrecy becoming the new norm? Are we entering an era where space agencies prefer silence over transparency? When the desire to control the narrative outweighs the tradition of open scientific inquiry? Or is this merely a temporary deviation, the strangeness associated with a specific observation? Perhaps normal processes will resume when the data becomes clearer. For now, we have no answers, but we have questions, and these questions multiply with each day of silence. If this silence continues, if no new information appears from agencies around the world, then the worst scenarios begin to gain more significance. Not because it is likely, but because human psychology fills voids with fears. In the next part, we will confront this worst-case scenario directly, not to endorse it, but to understand why it becomes psychologically, if not scientifically, inevitable when information disappears behind the walls of institutions. The fifth part is the worst scenario. Let's be clear, if this silence continues, if agencies keep withholding or saying nothing substantial, the hypothesis of aliens will become psychologically inevitable. Not scientifically proven, not even scientifically probable, but inevitable, in the sense that the human mind begins to move in this direction, constructing a narrative that gives meaning to this silence, as we are beings that create stories. When we lack data, we create stories. And the tale of alien visits is one of the most powerful narratives our species has ever created. Let's outline what the worst-case scenario might look like, not as a prediction, but as a thought experiment. Imagine that an object with 3 eyes is not a comet. Imagine it is an artifact, something created by an intelligence and sent into space with purposes we do not yet understand. Suppose agencies have recorded signs, characteristics, and behaviors that do not fit within natural explanations. There may have been spectroscopic anomalies, emission lines that do not correspond to the known composition of comets. Perhaps there were subtle course corrections, slight changes in trajectory that cannot be explained by gas emissions or gravitational interactions. Perhaps during its passage behind the sun, in the period of occultation when we could not observe it directly, something occurred that changed its speed or direction in ways that disrupted the usual patterns of comets. Now imagine that this object moves along a trajectory that intersects with the Earth or its orbital path. Not immediately, not threateningly, but in a way that evokes a sense of intent and purpose. The worst scenario is not only that it exists, but that it is directed here, or transmits information here, or prepares something here. This would be a discovery that shatters all existing frameworks. Every assumption about our place in the universe would be reconsidered. Every question about whether we are alone in the universe will have an answer, and that answer will be frightening, not because aliens are necessarily hostile, but because the uncertainty will become unbearable. Let's put this in historical context. The scientific community has already faced false alarms. The WOW signal in 1977, a powerful narrowband radio signal captured by a large telescope, briefly appeared to be a possible alien message. It was never detected again and received no satisfactory explanation. It remains an anomaly, but is not proof of anything. The Lennon comet in 2011 became the subject of intense speculation. Many claimed it would cause earthquakes, changes in the magnetic field, or some other catastrophe. In the end, it disintegrated before perihelion. It turned out to be nothing. The hysteria dissipated. The process of revealing information about UFOs and unidentified aerial phenomena, which had developed gradually in recent years, offers a different model. Countries began to gradually release previously classified videos of aerial phenomena that are difficult to explain. They do it slowly, controlling the flow of information, allowing the public to get used to the idea that there are things in our sky that we do not understand before moving on to more significant revelations. This is a carefully thought-out process aimed at avoiding panic while acknowledging unpleasant truths. If the three-eyed atlas is something anomalous, perhaps a similar model is used. Agencies may prepare the ground, waiting for the right moment, trying to figure out how to communicate something without causing mass hysteria and undermining their own reputation. Because here's the thing. If you announce that you have discovered an artificial interstellar object, you cannot back down. One cannot say, "Oops, we made a mistake." After the whole world has absorbed that information, the stakes are too high to air, so the incentive is to be absolutely certain before saying anything. But outside, caution and secrecy look the same. The public cannot distinguish "we are cautious" from "we are hiding something," and the longer the silence lasts, the more the latter interpretation gains popularity. Conspiracy theories do not arise from nothing. They arise from the gaps between what people think they should know and what they are told. When these gaps widen, when silence stretches, when agencies offer certainty without providing data, conspiracy theories begin to form on their own. I want to be clear, this worst-case scenario is speculative. It is not a basic hypothesis, nor is it something that data currently confirms, but it is the logical endpoint under current conditions, a place where minds will question if silence continues and deepens. Understanding this psychological trajectory is important because it shapes how we interpret everything that follows. If people are inclined to expect the worst, they will perceive uncertainty as confirmation. They will see ordinary bureaucratic delays as evidence of truth being concealed. Perception becomes its own reality. We acknowledge this possibility as one branch of exploration, leaving it on the agenda not as a closed statement, but as an open question. Complete disregard, refusal to consider her, does not solve the problem. It only drives her into the shadows, where she becomes something less rational and less connected to evidence. It is better to bring it to light, to study and understand why it possesses psychological power, even if it lacks scientific confirmation. Now we delve into details, into data hidden beneath the noise, into anomalies that may be signals or just noise. In the next part, we will explore what amateur astronomers and professional observatories quietly report: orbital remnants, spectroscopic hints, whispers circulating under official silence. Because if silence is the public face, then noise is the private underpinning, and within this noise, there may be something worth attention. Part 6. Data hidden beneath the noise. Astronomy has always been a conversation between signal and noise. Every photon reaching our telescopes carries information, but the intervals between photons, moments of darkness, and statistical fluctuations are equally important, blurring the line between detection and imagination. When we look at 31 Atlas, we see not just an object, but streams of data, orbital models, spectroscopic signatures, remnants and tracking calculations. And in these remnants, in tiny deviations from predicted paths, some people see patterns. The small planet center keeps track of data on small celestial bodies. Both amateur and professional astronomers contribute their observations, which form the basis for increasingly accurate orbital models. For most objects, the matches are clear. Observations correspond to predictions within acceptable margins of error. However, in the case of 31 Atlas, some trackers noted strange remnants, small non-gravitational accelerations that do not quite fit the standard model of comet evaporation. These could be measurement errors or artifacts arising from combining data from different observers with varying equipment. Or they could be real deviations indicating that the object's behavior does not match our expectations. Non-gravitational forces are often encountered in comets. When ice sublimates on the sunlit side, it creates a thrust similar to a tiny rocket engine. This causes comets to accelerate or decelerate in ways not predicted by purely gravitational calculations. Astronomers have models for this and take these forces into account when refining orbits. The problem is that the magnitude and direction of these forces must correlate with the comet's distance from the sun, its rotational speed, and the distribution of volatile ice on its surface. If these correlations are not maintained, if the forces are too strong or too weak, or directed in unexpected ways, it raises questions. Some online forums where astronomy enthusiasts gather to share observations and discuss data processing methods are actively debating claims that an object called Tri-Eye Atlas exhibits unusual accelerations. One of the forum participants claimed that the object shows a change in speed that cannot be explained solely by the sublimation of water ice. Another suggested that the object's trajectory includes periodic adjustments, as if something regularly alters its course. These statements have not been verified. They are based on publicly available tracking data that anyone can download and analyze, but different analysts obtain different results depending on their data processing methods. At these levels of precision, noise, and signal mix. And there is also spectroscopy. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its gaze towards Tri-Eye Atlas during its approach. Messages came not directly from NASA, but from secondary sources citing unnamed researchers claiming that Webb recorded an anomalously high carbon dioxide to water ratio of about 8:1, significantly higher than typical comets. Carbon dioxide is found in comets, but such distorted ratios indicate an unusual composition, possibly formed in a different environment or a different type of icy mixture than we see in the comets of our solar system. Other spectroscopic hints are also circulating, possibly unexpected emission lines from organic compounds that do not conform to standard comet chemistry. Or these lines are merely noise, artifacts of atmospheric correction, features of the telescope's instruments reacting to a faint moving target. Discussions erupted in scientific literature and on preprint servers. Some astronomers consider these signals significant, while others insist they are calibration artifacts, a typical phenomenon when instruments operate at the edge of their sensitivity. The truth is probably somewhere in the middle, but without access to raw data and a complete analysis, outside observers cannot resolve these disputes. Let's consider what anomalies could indicate artificial origin. Non-thermal radiation would be an important sign. If the 3-Eye Atlas emitted light or warmth that could not be explained solely by reflected sunlight or thermal radiation from a warm surface, it would be very strange. Doppler shifts in spectral lines could indicate the rotation or movement of components, but strange patterns, such as periodic modulation suggesting the presence of structures or mechanisms, would warrant further investigation. Any radio emission would be an extraordinary event. Comets do not emit radio signals or organized frequencies. If we discovered a signal, any signal, coming from Tri-I Atlas, the conversation would instantly and completely change. But we have not discovered anything like this yet. At least nothing has been publicly announced. The existing signals are ambiguous. They are statistical whispers that may mean something or nothing. And this ambivalence is precisely where controversy lives. Some scholars see it as evidence worthy of further study, while others consider it mere noise, unworthy of attention. What observatories or telescopes might hold key data that has not yet been published? The JWST is certainly an obvious candidate, with its sensitivity to detect faint spectroscopic features that other instruments might miss. Ground-based arrays, such as the Very Large Telescope in Chile or the Keck Observatory in Hawaii, can also contribute optical and infrared observations if they are pointed in the right direction. The upcoming Vera Rubin Observatory, when fully operational, will be able to track thousands of faint objects simultaneously, automatically marking anything unusual. If a repeat of the object trio atlas appears, or if similar objects arise, Rubin will capture them at an early stage. But for now, we are stuck with fragments, pieces of data that do not form a clear picture. Some fragments indicate a normal comet operating in a usual manner. Others hint at something stranger, something that raises questions, and without a full set of data, without transparency from the agencies controlling the best tools, we cannot resolve the contradictions. We remain in ignorance, filling the gaps with speculation, wondering whether the anomalies are real or if we are seeing patterns in randomness because we want to see patterns. In the next part, we will again turn to the most provocative figure in this discussion, Avia Loevu. We will consider the arguments of a Harvard astronomer who built a career on taking anomalies seriously, how his ideas shape the narrative, and why his hypothesis evokes both fear and support, as well as equal skepticism. Because in science, personality matters. The message depends on who conveys it, and Loeb is a messenger whose opinions are as divided as rarely anyone else's. Part 7. Loeb's Hypothesis. A New Consideration. Avi Loeb is not a marginal figure. Let's clarify that right away. He is a Harvard professor, a former head of the astronomy department, who has published hundreds of articles in peer-reviewed journals and received numerous awards. He is a recognized scholar by any traditional measure, but he has also become something else, a lightning rod. Since Loeb is willing to discuss things that other astronomers think but do not publicly voice, he is open to hypotheses that go beyond what is considered respectful scientific discourse. This willingness has made him both a celebrity and a target. His fame began with Oumuamua. When this first interstellar object passed through our solar system in 2017, most astronomers classified it as an asteroid or comet and did not delve deeper into its study. Loeb examined the data and saw something that troubled him. The object's trajectory showed slight accelerations that could not easily be explained by gas emissions, as it showed no signs of such emissions. Its brightness varied, indicating an elongated shape rotating along its axis. Its speed and trajectory were what one would expect from an artificial object sent from another star, rather than a random stone ejected from a distant planetary system. Loeb suggested in his published article that Oumuamua could be a light sail, a thin reflective sheet moving under the influence of starlight or a laser, a technology that humanity has already conceived but not yet created. This hypothesis was scientifically justified, mathematically precise, and theoretically verifiable. However, it also sparked a storm of discussions. The reaction of the scientific community ranged from cautious interest to outright hostility. Some praised him for his unconventional thinking, while others accused him of seeking attention, lowering the standards of scientific discourse, and legitimizing pseudoscience by considering exotic explanations when simpler ones were available. This context helps understand his position regarding the object Tri-I. Loeb actively speaks about it, asserting in published Q&As and public statements that we should take anomalies seriously rather than dismiss them thoughtlessly. His main assertions are as follows. The brightness of Tri-I implies the presence of a large object or a highly reflective surface. The trajectory, according to him, is too precise, too perfectly aligned with what one might expect from an object aimed at the inner part of the solar system, rather than a chaotic rotation. The absence of the expected coma or tail, as well as the uncertainty regarding these characteristics, does not correspond to the normal behavior of comets at such a distance from the Sun. He also proposes the possibility, not as a statement, but as a hypothesis, that the maneuvers could have occurred during an occultation behind the sun, when we could not observe the object directly, course changes that we would not have detected afterward. Loeb also points out the minimal or absent non-gravitational forces. For a comet the size of Triglass, approaching the sun, measurable effects of gas emission on its trajectory should be expected. The object must lose material, creating thrust, which would be reflected in the orbital remnants as deviations from purely capillary motion. If these forces are less than expected or not detected at all, it is worth studying. Either the object is made of something extraordinarily refractive that does not sublimate easily, or it is not made of ice at all. The scientific community's reaction to Loeb's arguments about the tri-eye was predictably mixed. Many astronomers believe that the observations still correspond to the comet, and the anomalies pointed out by Loeb can be explained by dust behavior, calibration uncertainties, or simply limitations of our data. One of the researchers was quoted stating that extraordinary claims require extraordinary evidence, and what we have are ordinary proofs of an ordinary object observed under complex conditions. Other researchers noted that interstellar space differs from the conditions in which the comets of our solar system formed, so we should expect differences in composition, unusual mixtures of ice, and behaviors that do not conform to our local patterns. This dispute has a political dimension in the academic environment that cannot be ignored. Exotic hypotheses attract attention, receive media coverage, lead to book contracts, and invitations to speak at conferences. However, they also provoke skepticism and professional risks. If you make a mistake in something exotic, you damage your reputation much more than if you err in something mundane. The review process in leading journals becomes more complicated when your hypothesis is controversial. Funding organizations are cautious in supporting research that may be perceived as speculative or unserious. The structure of incentives in modern science leans towards conservatism, favoring explanations that fit established frameworks and a reluctance to step outside the familiar. Loeb realizes these dynamics. He has written a lot about it, claiming that science has become too conservative, too quick to dismiss anomalies, and adheres to consensus thinking. He positions his approach as Galilean, returning to a time when scientists were willing to challenge established beliefs based on observational data. His critics view his approach differently, as a desire for attention, a lowering of standards, a blending of possibility with plausibility that misleads the public. But there is truth in it as well. Regardless of whether his specific hypothesis works, anomalies compel us to refine our methods. Even if 31 Atlas turns out to be an entirely ordinary comet with a slightly unusual composition, the process of its study, the exclusion of exotic explanations, and the attempt to push our tools and models to the limit, all of this makes us better scientists. We learn more about what comets can be like, how interstellar conditions differ from our local environment, and what signs we should expect from truly anomalous objects if they ever appear. Loeb often uses a lesson-based approach. He claims that we should use objects like 31 atlases as learning opportunities to ponder what we would seek if we were searching for extraterrestrial technologies. What signs might there be? How would we distinguish artificial objects from natural ones? What observations could unequivocally confirm or refute the existence of intelligence? These are quite reasonable scientific questions, worth investigating, even if in this case we are dealing only with a comet, because the next object might not be like this one, and if we haven't thought through the methodology, if we haven't prepared mentally and technically, we might miss it or dismiss it without proper analysis. The tension between Loeb and the broader scientific community reflects a deeper issue regarding how science should operate. Should we be conservative, demanding irrefutable evidence before considering exotic explanations? Should we be more open to considering unusual hypotheses if they are testable, using them for observation and analysis, even if they are unlikely? Both approaches have their merits and risks. Excessive caution can lead us to miss true discoveries as they do not match our expectations. On the other hand, excessive openness wastes time and resources chasing illusions, undermining scientific credibility with speculation. The atlas with 3 eyes is somewhere in the middle of this tension. It is strange enough to attract attention, yet ordinary enough to be dismissed. The forehead and similar features urge us to examine the subject more closely. Critics pull us back to its neglect, and somewhere in between, the truth likely awaits better data to reveal itself. But this data must be gathered, observations must be made, and someone must be ready to look at it, even if the gaze may prove erroneous. In the next part, we will change the perspective and see who else might be observing the atlas with three eyes. Players besides government space agencies, private observatories, commercial networks, organizations that may have noticed something but chose to remain silent for their own reasons. In the modern world, observing space is not a monopoly. Tools are distributed, there are many observers, and information does not always go through official channels. Part 8. Hidden Players. The romantic image of astronomy is a solitary scholar at a telescope, gazing into the night sky with a notebook in hand. This image is outdated. Modern astronomy is industrial, networked, and automated. Telescopes scan the sky, continuously transmitting data streams that process millions of observations each night. And not all of these telescopes are state-owned. Not all data goes through official channels. The democratization of space observation has created a parallel universe of observers, some of whom may know things not included in press releases. Private observatories have proliferated in recent decades. Wealthy individuals, universities, and research consortia built facilities that can rival government institutions. The last bulky observatory controls a global network of robotic telescopes that can perform individual observation tasks. Planetary Resources, before switching from asteroid mining, was developing methods for tracking small bodies using commercial imaging systems. Astronomy enthusiasts equipped with CCD cameras and modern software regularly discover new supernovae, asteroids, and comets. The line between professionals and amateurs has blurred to the point that the distinction is more about funding than capabilities. Could any of these private organizations observe the three-eyed atlas in such a way as to notice something unusual? It is quite possible. A well-equipped amateur with a 16-inch telescope and a cooled CCD camera can detect objects that were inaccessible to professionals 50 years ago. Networks like the Minor Planet Center of the International Astronomical Union rely on contributions from amateurs to gather observational data. If someone noticed something abnormal, such as a structural anomaly, unexpected radiation, or deviation from the predicted position, they could report it through official channels or keep the information to themselves, being confident in what they see but unwilling to make claims without confirmation. There are rumors, whispers, and online forums that are often deleted. Someone claims to have captured an image of the three-component atlas object, showing a branching structure as if the object split or has multiple components. This post is criticized. Debates arise about the artifacts of the image and real features, after which the author deletes everything. Another user claims that their automatic camera covering the entire sky captured an anomalous bright event, a sharp burst of luminosity that does not match collision or gas emission models. And this post also disappears. Are these genuine observations that have been suppressed or self-censorship by nervous observers, or removed by moderators seeking to control speculation? Or are they forgeries trying to attract attention, exposed and removed out of shame? We cannot know without access to the original data, and this is the problem. In the information age, data can disappear as easily as it appears. Screenshots prove nothing. Testimonies hold no weight without confirmation. The signal-to-noise ratio in online astronomical communities is high, making it difficult to separate true reports of anomalies from the noise. Now let's broaden the scope. Companies engaged in space flights have assets in orbit that are not primarily scientific instruments but can potentially observe deep space objects. SpaceX manages thousands of stylized satellites. Blue Origin is developing orbital infrastructure. Chinese private space companies are launching commercial payloads. These satellites are equipped with cameras, sensors, and communication arrays, most directed at Earth or each other, but some have wide-angle cameras for navigation, monitoring space debris, and ensuring situational awareness. Could any of these systems capture the three-component atlas? The geometry would have to match perfectly. The object must pass through the satellite's field of view at the moment when the camera was active and the exposure settings were suitable for detecting faint objects. It's unlikely, but not impossible. And if it happened, if a commercial satellite captured an image of an interstellar object with something unexpected, what would the company do? Would they publish it? Sell it? Keep it secret? Use it for internal research? Commercial organizations have no legal obligation to share astronomical data. They can do whatever they want with their observations. There is also the possibility of secret experiments with radars or LIDAR. Deep space radar theoretically can detect and profile objects at significant distances, much farther than optical telescopes can resolve details. The Arecibo telescope, before its collapse, could reflect radio signals from asteroids near Earth and create detailed maps of their surface. There are also smaller systems, some managed by defense agencies, others by scientific institutions, and some by organizations that do not advertise their capabilities. If the 300th asteroid Atlas passed close enough to Earth and someone directed a powerful radar system at it, it might be possible to obtain images with Doppler radar showing its shape, rotation, and surface features. Will such data be publicly available? Probably not. Radar systems used for observing space often have dual purposes, meaning they also track satellites, space debris, and potentially hostile spacecraft. The capabilities of such systems are classified. If they were monitoring the 300th asteroid Atlas, then this data will likely be classified not because the object itself is secret, but because revealing the data will show the capabilities of the system. This is standard operational security, not a conspiracy. But outside, it creates another black box, another place where information can exist, but remains hidden. Communication satellites also play their role. These satellites monitor vast ranges of the radio spectrum in search of signals, interference, and anything that might affect their operation. If the 300th asteroid Atlas emitted radio waves, even weakly and occasionally, a communication satellite could register it as normal background noise. Again, the question, will this data be publicly available? Communication companies are not engaged in astronomy. They have no reason to analyze or share such data unless it directly impacts their services. Such data may be stored in logs somewhere, unexamined and unregistered. Historical analogies help to understand the situation. During the Cold War, early satellite images were classified for decades. The technology of photographing Earth from space was revolutionary, and governments did not want adversaries to know about the resolution, coverage, and capabilities. Dual-use data, information with both scientific and military applications, is processed with caution. The 300th asteroid Atlas is not a military target, but the systems used to observe it may be sensitive, and this sensitivity creates obstacles to transparency. Thus, we are left with a situation where information may be on corporate servers, in classified databases, on enthusiasts' hard drives, in logs and caches that no one thought to explore or share. The official version, as presented in press releases and scientific articles, always remains incomplete. It is just the tip of the iceberg. Beneath the surface exists an entire ecosystem of surveillance and data that never becomes part of public discourse. Can some participants already know more than the public? Can they wait for the moment to reveal or monetize this information? Incentives vary. A corporation may wait for the right moment to announce an opening, using it for marketing or attracting investments. Defense agencies may never disclose information, hiding data in inaccessible archives. An amateur may possess something significant, but lack the authority or platform for it to be taken seriously. The information ecosystem is fragmented, and such fragmentation creates gaps where data is hidden. In the next part, we will explore why world powers may choose strategic silence instead of open disclosure of information. We will move from technical capabilities to strategy, politics, and the complex calculations that governments make when faced with data that could undermine society or reveal opportunities they would prefer to hide. Because silence is not always uncertainty. Sometimes it's a matter of control. Let's ask the uncomfortable question directly. Why can governments or space agencies remain silent about the three-eyed Atlas if they know something important? We have already discussed this question in several parts, but it's time to look at it directly. Not because conspiracy theory is the most likely explanation, but because understanding the motives for secrecy helps us interpret observed patterns. States do not act solely on scientific principles. They are guided by strategic calculations, risk assessments, and political considerations that are not always related to the truth, but are entirely about control. The primary motive is control over the narrative and societal reaction. States are obsessed with managing the flow of information to the populace. This is not necessarily sinister. It is based on the belief, sometimes justified and sometimes not, that people may panic or react inadequately if given certain information without proper context. If the three-eyed atlas indicates signs of artificial origin, imagine the reaction. Financial markets will likely begin to fluctuate due to uncertainty about humanity's future. Religious institutions will try to integrate this information into their worldviews. Political movements can arise around competing interpretations, some demanding immediate disclosure of all information, others preparing for potential threats. Managing this chaos is a powerful incentive to remain silent until a clear and controlled message emerges. The second motive is to avoid mass speculation. Even without specific evidence of anything anomalous, the mere suggestion that an interstellar object might be artificial will provoke speculation surpassing any existing proof. We have seen this in the case of the disclosure of unidentified aerial phenomena. The Pentagon released a video of aerial phenomena that could not be explained, and immediately public discussion shifted to aliens, despite officials trying to avoid such statements. In the case of the three-eyed atlas, if agencies hint at something unusual, speculation will flare up, and rolling it back will be nearly impossible. It's better to stay in the shadows until the level of confidence is high enough to replace speculation with facts. The third motive lies in protecting sensitive interests in defense or communication. Space observation systems have dual purposes. They monitor asteroids but also track satellite debris and potentially hostile spacecraft. If the Three Eyes of Atlas system were monitored by secret systems, revealing what they saw could demonstrate their capabilities, resolution, and sensitivity. Opponents note what becomes known and can restore technologies based on published data. Protecting these capabilities may require keeping observations secret, even if the object itself is of scientific interest. The fourth motive is the desire to gain time to confirm or refute data. Scientific research requires time, as does the process of verification. If the initial observation indicates something anomalous, the responsible organizations will want to verify, recheck, and double-check the information before making public statements. They will need multiple independent confirmations. It is necessary to exclude artifacts, instrumental errors, and incorrect interpretations. This process may take weeks or months. During this time, silence will be the most cautious and safe choice, even if it causes public discontent and fuels rumors. The fifth motive is diplomatic and strategic positioning. If the Three Eyes of Atlas system is truly significant and represents something anomalous, different countries may strive to gain a favorable position before the information becomes public. Perhaps China needs to complete its analysis before NASA announces its findings to avoid appearing reactive to American statements. Perhaps the United States wants to coordinate its actions with allies before going public, ensuring a unified message. These strategic calculations may delay the disclosure of information, not due to a conspiracy, but because of the complex game of international relations. Now let's consider the possibility of a black budget. Defense agencies worldwide manage programs that are not reflected in public budgets, have minimal oversight, and exist in legal gray areas. The U.S. Department of Defense has historically conducted tracking programs for objects in space, both terrestrial and extraterrestrial. The Threat Identification Program in Aviation, known since 2017, was one such program focused on aerial phenomena. Are there similar programs that focus on deep space objects? Almost certainly. They may be called differently, hidden within larger initiatives for observation or reconnaissance, but such a possibility exists. If such a program discovered something significant regarding the Three Eyes of Atlas, would we learn about it? It solely depends on what they discovered and the strategic value of that information. If it is scientifically interesting but lacks strategic significance, it may ultimately be declassified and published. If the information has strategic consequences, affects national security, or reveals sensitive collection methods, it may remain closed forever. We would never know. The absence of information is not proof of its non-existence, especially regarding secret programs. Historical examples help to understand these dynamics. The Galileo Project, Avi Loeb's initiative to search for extraterrestrial technologies using open scientific methods, partially arose in response to the tension between open science and secret surveillance. Loeb argues that too many observations of space occur behind walls of secrecy, limiting scientific research. During the Cold War, reconnaissance satellites were so classified that their existence remained a secret for many years. The data they collected, even when scientifically valuable, remained inaccessible. UFO and unidentified aerial phenomenon study programs throughout the 20th century operated with minimal oversight, publishing information only occasionally and often under pressure from leaks or freedom of information requests. It is clear that when information intersects with national security, even indirectly, transparency suffers. And the atlas with three eyes, despite being a natural object, intersects with space observation systems that are clearly related to national security. This intersection creates barriers to openness. Let me present a hypothetical scenario. Imagine that a secret discovery has occurred, observed by a system that officially does not exist, or whose capabilities are not publicly known. This observation captures something unexpected, possibly surface features inconsistent with the comet, perhaps weak radiation at an unexpected wavelength, or changes in trajectory that require explanation. What happens next? First, the data is marked and sent for review. Someone decides that this is important enough to inform higher management. Secondly, an inspection begins. They engage other systems, trying to confirm the data with independent sensors, checking for instrumental artifacts. Thirdly, if the verification is confirmed, discussions begin about what to do with the obtained information. Legal experts assess the classification requirements. Scientific advisors analyze whether civilian astronomers can independently discover the same. Strategic planners consider geopolitical consequences. Public relations services begin preparing possible statements, planning how to manage information disclosure if necessary. This process takes time, often weeks or months. During this time, organizations with public access, such as NASA, may be informed, but they will be limited in what they can say. They cannot refer to classified observations. They cannot hint at sources of information they should not acknowledge, so they remain silent or provide vague assurances based only on open data. From the outside, it looks like concealment or incompetence. From the inside, it is a standard procedure. Ultimately, one of several outcomes occurs. Either the anomaly is explained as an instrumental error or a natural phenomenon, and the information remains hidden because there is no reason for its declassification, or the anomaly persists, gains weight, and a decision is made for controlled disclosure. In such a scenario, information will be gradually published, carefully crafted, coordinated between agencies, and possibly between states. The public will be told a true but incomplete story, created to inform without revealing sensitive capabilities. Is this happening with the three-dimensional atlas? We have no evidence of this, but there is also no evidence to the contrary. The infrastructure for such scenarios exists. There are precedents. The motives are also evident. Whether these elements connect in this case remains a guess, but these are fact-based assumptions, not paranoid fantasies. Counter-arguments matter. The pressure of transparency is real. In democracies, governments face scrutiny, leaks, whistleblowers, and journalists digging into hidden stories. Peer review creates its own imperatives for transparency. If NASA scientists know something significant, many of them will want to publish their findings to share with the community, regardless of official preferences. Leaks happen. Pentagon documents became known due to leaks. Edward Snowden revealed secrets. Secret space programs were exposed through leaks and investigations. Perfect secrecy is almost impossible to maintain in the long term, so if there is something important, if agencies hold anomalous data, silence likely cannot last forever. Ultimately, someone will speak, someone will leak, someone will publish information. The question is, how long silence can be maintained before it is broken, and what happens to information during that time? In the next part, we will completely change the subject. We will move from intrigue to theory and ask, if the three-dimensional atlas is an alien artifact, what does its silence tell us about its design, purpose, and limitations? We will enter the realm of speculative physics, exploring what the silence of the probe can tell us about its creators and their intentions, because sometimes the absence of a signal is the signal itself. Part 10. Speculative Physics of Silence. Let's conduct a thought experiment. Let's assume for a few minutes that the three-dimensional atlas is not a comet. Let's assume it is an artifact, a probe sent by an intelligence from another star system. Now let's ask the question, what does its silence tell us? Not about the silence of governments, but about the silence of the object itself. Why does the interstellar probe, intended for research or observation, remain silent? Not emitting signals, not trying to establish contact with us, appearing only as a vague, blurry spot in our telescopes? The first answer is secrecy. If you want to observe without being noticed, you need to minimize every detectable signature. No radio transmissions, as they will announce your presence from great distances. No unnecessary heat emissions, since heat can be detected in the infrared spectrum. No bright surfaces or reflective panels, as they will attract sunlight and attention. The design should aim for minimal visibility to resemble a natural object. The stealth probe will have a dark, non-reflective body. Its surface can be covered with a material that absorbs rather than reflects light. It can use passive cooling, slowly radiating heat in directions hidden from potential observers. This approach is justified if the goal is observation without interference. Perhaps the probe developers want to study civilizations without contaminating the research, avoiding the variable of contact in the equation. We apply such methods ourselves in observing wildlife. We use camera traps, remote sensors, and other techniques that allow us to monitor animals without revealing our presence. A probe operating on this principle remains hidden, collecting data silently and reporting back through undetectable channels. The second aspect is energy conservation. Interstellar travel requires enormous energy expenditures. Accelerating even a small object to a significant fraction of the speed of light demands colossal resources. The probe may not have enough fuel or power for active signal transmission, especially if it is designed to operate for centuries or millennia. Instead, he can rely on passive data collection, accumulating information while waiting for a meeting with another probe or mothership, or simply recording data for his own needs without demanding immediate transmission. Passive energy extraction aligns with this model. The probe can collect energy from sunlight using ultra-efficient solar panels, extract particles from the interstellar medium, or even utilize the radioactive decay of embedded materials for a slow and steady energy supply. All these methods provide a limited amount of energy, sufficient for basic functions but not for high-power transmissions. The probe remains silent because it has no choice. It operates under a limited budget, where every function is optimized for efficiency rather than communication. The third aspect is autonomy, managed by artificial intelligence with specific mission parameters. Imagine a smart probe equipped with AI capable of making decisions but limited by programming that defines its behavior. His instructions may be simple. Observe, but do not engage. Collect data on planetary systems, on technological civilizations if encountered, but maintain distance. Report findings only under certain conditions, or not at all if the mission is purely archival. Artificial intelligence in the probe does not experience curiosity or desire. It follows programming. If that programming says, "Be silent," it will be silent. This relates to concepts from critical situation theory and the Fermi paradox. The zoo hypothesis suggests that extraterrestrial civilizations may consciously avoid contact with us, viewing Earth as a nature reserve, observing but not intervening. A probe designed to operate under the parameters of the zoo hypothesis will be created for observation without contact, which explains both its presence and silence. This is also related to the hypothesis of secrecy. Perhaps the probes are scattered throughout the galaxy, lying dormant and waiting for specific triggers to activate, possibly linked to technological advancements when a civilization reaches certain capabilities. Perhaps the trigger is the signal we must send. Until the trigger condition is met, the stealth probe remains silent. Cryptographic or quantum communication offers another explanation. If the probe transmits data using methods we cannot yet detect, its communications will remain invisible to us. Quantum entanglement may allow instant communication without classical signals traveling through space. High-directional, low-power laser links can transmit information in narrow beams that we will never intercept unless we are in a direct line with the target. Spread spectrum techniques can distribute a signal over such a wide range of frequencies that it will appear as noise if you do not know the key to decode it. Human radio waves and television broadcasts penetrate into space, creating a detectable signature for any civilization with sensitive receivers. But it is ineffective. It is equivalent to shouting when one could whisper. An advanced civilization would likely use communication methods that minimize leakage and direct information precisely where needed, wasting no energy broadcasting into the void. From our perspective, such communications would be indistinguishable from silence. The probe can be talkative, just not in a way we can hear. Energy constraints highlight why silence might be the optimal strategy. Interstellar space is cold, close to absolute zero. Any active system generates heat, and it is difficult to dispose of this heat without noticeable radiation. A probe can use radiators directed away from potential observers, dissipating heat into the cosmic microwave background. It can operate at very low power, slowly processing data and waiting for long intervals between active phases. Minimizing heat, emissions, and any detectable signatures serves both stealth and efficiency. Could this explain why we see only a faint spot? Perhaps this spot is intentional, a minimal surface reflecting enough light to appear like a comet, while the actual structure of the probe is hidden beneath layers of dust or ice. Natural camouflage accumulated during the probe's journey through interstellar space, or perhaps a blur, is a cloud of particles generated by the probe for its concealment, a dust screen making detailed imaging impossible. We observe the camouflage, not the object itself. These ideas are speculative but based on physical principles rather than fantasies. We can create probes that minimize emissions. We know about stealth technology, passive observation, and energy constraints. Extrapolating these principles to an interstellar context is quite reasonable. It's a way to conceptualize the possible considering known laws of physics. This does not prove the artificial origin of the three-eyed atlases, but it helps to imagine what artificial might look like so we know what to search for. Such reflections serve their purpose. They refine our observational strategies. If we assume that the probe can use quantum communication, we develop quantum detectors. If we think it can emit thermal waste in certain directions, we place observers to catch these emissions. If we believe it can hide under dust, we create technologies to penetrate it using radars or other long waves. Even if the three-eyed atlases turn out to be just comets, contemplating such scenarios will prepare us for real events should they ever occur. Now we will briefly divert from the three-eyed atlases. We will explore a broader front of science in the year 2025, examining other anomalies, other silences, other places where the cosmos whispers, and we try to decipher these whispers. The fact is that three-eyed atlases do not exist in isolation. They are part of a broader scheme of mysteries, discoveries, and questions that define our current moment in scientific history. Understanding this context helps us see the three-eyed atlases more clearly and understand how they fit into the larger picture of our cosmic awakening. Part 11. Solar Superstorms and Hidden Risks. The sun tried to remind us who is in charge in May and June of 2025. Coronal mass ejections, massive eruptions of plasma and magnetic fields from the surface of the sun, struck the Earth's magnetosphere with such force that they triggered global geomagnetic warnings. Auroras danced at latitudes significantly further south than usual. Satellite operators rushed to protect their assets. Energy grid managers nervously monitored the situation, ready to implement emergency protocols if things worsened. For several days, the threat was real, not existential, but significant. It was an event that could disable communication satellites, disrupt the global positioning system, damage transformers and power grids, and leave regions without power for weeks or months. A coronal mass ejection is something imperceptible. The sun emits billions of tons of charged particles into space at speeds approaching 1,000,000 miles per hour. When this cloud of plasma collides with the Earth's magnetic field, the field compresses, oscillates, and induces currents in any conductive material, including long power lines and pipelines. The Carrington event in 1859, the most powerful geomagnetic storm in recorded history, caused currents so strong that telegraph systems sparked and caught fire. If such an event were to happen today, with our significantly more complex and vulnerable infrastructure, the damage could amount to trillions of dollars, affecting billions of people. But this is why it matters to our story. Cosmic threats exist on the spectrum, and agencies approach them conservatively. The sun is predictable in some aspects and extremely unpredictable in others. We can observe coronal mass ejections leaving the sun and calculate when they will reach Earth, but we cannot always predict their intensity or exact magnetic orientation, which determines the damage they will cause. Despite this uncertainty, space weather agencies issue warnings, forecasts, and alerts because the threat is clear, the physics is known, and the response protocols are established. In contrast, the situation with the Object 3 AI Atlas. This body, which we do not fully understand, exhibits behavior that can be both anomalous and ordinary, approaching through the inner solar system without a clear threat, but with many uncertainties. How do agencies cope with this situation? They act cautiously, which means they speak very little until they learn more. They do not want to alarm the public about something that may turn out to be insignificant. They strive to avoid panic or speculation without concrete evidence of danger or significance, so they prefer silence or silent reassurances that contain nothing substantial. This is a pattern. Known threats provoke communication, while unknown or ambiguous threats generate silence. It is a risk management strategy. Talking about a coronal mass ejection is safe because everyone understands that the threat is natural, temporary, and manageable. The discussion of an interstellar object that may be anomalous opens doors to questions that agencies are not ready to answer. What if it is artificial? What if it changes course? What if there are more? Better to remain silent than to provoke these questions prematurely. New research in solar weather forecasting conducted in the year 2025 helps to more accurately predict the severity and ways to mitigate the consequences. Machine learning models trained on long-term solar observation data can now predict coronal mass ejection intensity with improved confidence. Satellite constellations continuously monitor the sun from different angles, providing stereoscopic images that help predict how ejected material will evolve as it moves toward Earth. These achievements give us more time for warnings, more accurate forecasts, and a better opportunity to protect infrastructure. And this information is openly published, discussed at conferences, and integrated into public forecasting systems. Why such a difference? Because sunny weather is a known quantity, a threat we have tamed through understanding. The three atlases represent the unknown, wild things we have yet to learn to control, and people, including scientists and bureaucrats, react differently to the unknown and the known. The unknown is quarantined, kept at a distance, examined carefully before being integrated into public discourse. Space is noisy, signals constantly bombard us, radio waves from distant galaxies, neutrinos from supernovae, gravitational waves from colliding black holes, the hiss of cosmic microwave background radiation. Most of this noise we ignore because it is expected, fitting into our models. But when something does not fit the usual frames, when a signal challenges our perceptions, the noise becomes deafening, but in a different way. This is the noise of speculation, competing interpretations, uncertainty that cannot be resolved. And sometimes the response to this noise is the desire to remain silent until clarity emerges. The Atlas of Eyes is one note in this cosmic symphony. Solar storms are another. In the next part, we will delve into the whispers of dark matter, another cosmic anomaly existing on the edge of detection and confirmation, where physics collides with the limits of what we can observe and understand. The universe is full of things we cannot see directly. We can only infer them by their effects, and dark matter is the greatest invisible presence of all. Part 12. Dark matter, signal, hint. Deep underground, shielded from cosmic rays by kilometers of rock, detectors wait in the dark. These devices are cooled to near absolute zero temperatures, watching for something that may never appear. They are searching for dark matter, an invisible substance that makes up 85% of all matter in the universe, but has never been directly detected. We know of dark matter's existence because we can see its gravitational effects. Galaxies spin too quickly for the visible matter they contain. Groups of galaxies stay together despite the lack of mass in stars and gas. Gravitational lensing distorts light as if more mass is required than we can see. There is something there, something with mass, something that neither emits nor absorbs light. We call it dark matter, but it's just a temporary name for our ignorance. In the year 2025, whispers began to emerge from underground laboratories. Unconfirmed discoveries, unpublished results, and anomalies, clusters of events that did not quite align with expectations. One detector in Italy, a collaboration of Yaston or one of his subsequent experiments, reported an excess of events in a certain energy range. The excess was small, barely statistically significant. It could be explained by contamination, calibration shifts, or random fluctuations, but it was there. Consistently over several data series, enough for physicists to take notice, but not so much as to become overly excited. Dark matter particles, if they exist, would pass through ordinary matter almost without interaction. Only occasionally, perhaps once every few months, in a ton of detector material, a particle of dark matter will collide with an atomic nucleus, producing a tiny flash of light or a slight release of energy. This is exactly what these underground detectors are designed for. To capture these incredibly rare collisions, signals so weak that they barely rise above the noise. To distinguish the true dark matter signal from background noise, years of data, precise calibration, and multiple independent confirmations are needed. The whispers of the year 2025 are not confirmations. They resemble alluring hints, possibilities that require more time, more data, and more thorough analysis before anyone can claim a true discovery. But it is not empty. These are the very anomalies that make physicists check their instruments, reanalyze data, and ponder whether they are seeing the first faint trace of something real. To explain this to a broad audience, imagine trying to hear a whisper in a crowded stadium. This whisper is dark matter. The noise of the crowd is background radiation, cosmic rays, the radioactive decay of the detectors themselves, and all other energy sources creating signals. To hear the whisper, one must minimize the noise of the crowd. You descend deep underground to block cosmic rays using ultra-pure materials to minimize radioactive contamination and cooling everything to reduce thermal noise. You activate the detector for years, accumulating data, hoping that the statistics will improve enough for a real signal, if it exists, to emerge from the noise. Now connect this to the project 3i Atlas. Both stories talk about signals hidden in noise, anomalies that could be something or nothing, and the difficulties of distinguishing the real from the artifact when working at the limits of detection capabilities. Experiments in dark matter search are developed considering this problem. They include redundancy, various confirmation methods, and strict statistical thresholds before declaring a discovery. This process is slow, thoughtful, and conservative. Astronomy cannot always afford such luxury. 3i Atlas passed through the inner solar system on a schedule we could not control. We had one opportunity, perhaps a few weeks of optimal observation, and then it vanished. The collected data is all we have if he doesn't return, which is unlikely given his hyperbolic trajectory. Therefore, the standard of proof is different. We cannot wait years for confirmation. We need to work with what we have, interpret it as best as we can, acknowledge uncertainty, but still draw conclusions. This creates asymmetry in how discoveries are announced. Experiments in the search for dark matter can afford to wait before saying, "We have seen something interesting, but we do not yet call it a discovery." Astronomers observing a transient object do not have such an opportunity, but they also feel strong pressure not to exaggerate or declare something dramatic that may later turn out to be a mistake. As a result, a kind of compromise emerges, where they speak very little, waiting for a consensus that may never come because the object has already disappeared. The similarity is striking. We live in a universe full of signals, many of which are hidden, uncertain, and buried in noise, where extraction requires complex techniques and patient analysis. 3i Atlas could be an exception, an interstellar visitor that should be obvious and generate clear and unambiguous data. But what if it is not? What if it is just another whisper in the stadium, and we are trying to hear it amidst all the other noise? Here lies a philosophical question. How many anomalies do we pass by because they do not fit the accepted picture? Dark matter was an anomaly for decades before it became mainstream. Fritz Zwicky proposed it in the 1930s based on observations of a galaxy cluster. He called the missing substance Dunkel Materie, which translates to dark matter. The scientific community largely ignored him. Only in the 1970s, when Vera Rubin's measurements of rotation curves made the question undeniable, did dark matter enter the scientific mainstream. Decades of anomalies were dismissed or explained away until the weight of evidence became too great to ignore. Can the 3i Atlas follow a similar path? This is an anomaly that is currently dismissed or minimized, but future observations or reanalysis may reveal its significance, or conversely, an anomaly that seems interesting now, but will be explained as our understanding deepens. We will not know this for many years, possibly decades. The story of dark matter teaches us that sometimes patience is required, that not every anomaly is resolved quickly, and that some mysteries take generations to solve. But the story of dark matter also speaks to the sociology of science, about how anomalies that challenge existing concepts are met with skepticism until they can no longer be ignored. Zwicky was right, but he was considered eccentric, and his ideas were not taken seriously during his lifetime. Rubin faced gender-based discrimination against a backdrop of scientific skepticism. The path from anomaly to accepted fact is not smooth. It is fraught, politicized, and influenced by factors unrelated to the data itself. 3i Atlas exists within this sociology. Claims about his anomalous nature go through the same dynamics as claims about dark matter. Who makes this claim? What is their reputation? How does it relate to existing theories? What are the political and professional risks associated with its serious perception? These questions shape how anomalies are perceived, regardless of their actual validity. In the next part, we will introduce a new player: artificial intelligence. Artificial intelligence is changing the approach to processing astronomical data, identifying anomalies, and deciding what deserves human attention and what can be ignored. This transformation has deep implications for stories like 3I Atlas. As artificial intelligence systems increasingly analyze new data first, selecting what to elevate and what to reject, this adds a new level of complexity to the questions of silence and signals. Part 13. The role of artificial intelligence in space observation. The universe generates more data than humans can process. Every night, telescopes around the world capture millions of images. Every second, radio telescopes record gigabytes of signals. Spectroscopes produce thousands of spectra. The volume of data is overwhelming, far beyond what astronomers can study individually. We created Sentinel systems, artificial intelligence that processes vast streams of data, highlights the interesting, and filters out the unnecessary. These systems became the central infrastructure, the first line of analysis between raw data and human perception. The 500-meter aperture telescope in China, the world's largest single radio telescope, has been upgraded using artificial intelligence specifically designed to search for anomalies. The system analyzes incoming radio signals in real time, comparing them to samples from known sources and marking anything that doesn't match. It looks for transients, bursts, patterns that may indicate technological signals. Similar systems are being implemented in other institutions. The future Vera Rubin Observatory will use machine learning to process its massive survey data, automatically identifying supernovae, asteroids, variable stars, everything that changes or appears unexpectedly. NASA integrated artificial intelligence into several data streams. The James Webb Space Telescope uses machine learning to optimize its schedule, determining which targets to observe and when, balancing scientific priorities with operational constraints. Ground-based observations use neural networks trained to distinguish asteroids from stars, real objects from artifacts, interesting transients from boring background fluctuations. Artificial intelligence does not make final decisions, but it narrows the scope, directing human attention to a small portion of data that deserves careful examination. This is effective and even necessary. Without these filters, we would drown in data, missing important discoveries lost in the noise. However, this also creates a new vulnerability. What if artificial intelligence filters out something important? What if its training data does not include examples of a new phenomenon and it is mistakenly classified as uninteresting? What if the truly anomalous signal, the one we are most interested in, is marked as an error and automatically discarded? Machine learning systems learn from examples. You show them thousands of images of asteroids, teach them to distinguish asteroids, and they learn to recognize them. But they also learn what things do not look like asteroids and tend to classify everything that does not fit their training set as noise or artifacts. If the 13th onboard telescope shows characteristics different from any comet in the training set, the artificial intelligence system may classify it as suspicious or reject it as corrupted data. The result depends on how the system was trained, its confidence thresholds, and how it handles edge cases. Here is a hypothetical scenario. Imagine an artificial intelligence system processing images from Mars orbiters using the approach of the 13th onboard telescope. The system sees a faint object, attempts to classify it, and discovers that it doesn't quite fit known categories. She assigns him a low trust level, marks him as a potential artifact, and places him in the low priority queue. By the time the person notices, weeks have passed, the observation window is closed, the object is gone, and the artificial intelligence did not suppress the information intentionally. He simply followed his program and ingrained biases about what is real and what is noise. However, the effect is the same as with deliberate suppression. Information that should have surfaced is buried. Let's consider the opposite scenario. The artificial intelligence identifies a trigger object as highly anomalous, assigns it a high priority, and immediately relays it to human analysts. People analyze the data, see the same ambiguous information we discussed, and decide that the AI has exaggerated too much. They lower the priority, postpone it, and move on to more important tasks. Here, the AI did its job correctly, but the human filter killed the signal. The system failed not due to AI limitations, but because of overly conservative human judgment. These scenarios highlight the question, do we trust AI more than human observations? Each approach has its weaknesses. People have biases, limited attention, and a tendency to see what they expect to see. AI has limitations in training, an inability to generalize beyond its examples, and a lack of common sense in truly new situations. Ideally, we should use both approaches in complementary roles, AI for breadth and speed, people for depth and judgment. This requires good communication between systems, and such communication is not always perfect. There is another dimension, AI as a controller, in the sense of determining what becomes publicly available. If the AI system marks something as highly anomalous, but the anomaly is ambiguous or potentially sensational, the one controlling this system faces a choice: to immediately publish the finding, attracting public attention and scrutiny, or conduct a preliminary investigation before making a statement and controlling the narrative. Artificial intelligence has performed its task by marking the anomaly, but it is people who decide what to do with this signal. In the future, this dynamic will intensify. As AI systems become more complex and autonomously process more data, the role of humans will shift from direct observation to overseeing how AI monitors the data. When this happens, silence may become not human, but algorithmic, a consequence of how systems are designed and trained, rather than a conscious choice by scientists or administrators. This raises new questions about responsibility. If the AI system misses or suppresses something important, who will be held responsible? The programmers who developed it, the institutions that implemented it, or the training data that shaped its behavior? The three-eyed atlas was observed during the transitional period. Part of the data processing was automated, part manual, with some institutions using modern AI pipelines while others relied on traditional methods. This heterogeneity creates gaps, places where information can slip away or be lost in translation between systems. It is not necessarily anyone's fault. It is merely the tangled reality of infrastructure and transition. Old methods coexist with new ones, neither of which is perfect, and both bring various errors. In the next part, we will move from systems that detect signals to the nature of the signals themselves. In particular, we explore quantum communication, a breakthrough in technology that may explain why some signals remain invisible to us. Perhaps silence is related not to what is said, but to how it is said, in languages and through channels for which we currently have no dictionary to hear. Perhaps the three-eyed atlas is shouting, and we are simply not listening on the right frequencies. Part 14. Breakthrough in quantum communication. The year 2025 became a year of breakthroughs in quantum communication that most people barely noticed. Experiments with satellite entangled photons have achieved new distance records, demonstrating that quantum encryption keys can be transmitted between continents with nearly perfect security. Ground stations in China and Europe established quantum connections that could not be intercepted by traditional means. This technology transitioned from laboratory demonstrations to practical implementation, a quiet revolution in how information can be transmitted. For those unfamiliar with this topic, quantum entanglement utilizes the properties of entangled particles. When two photons are entangled, measuring the state of one instantly affects the state of the other, regardless of distance. This does not violate the theory of relativity, as a classical channel is still required to complete the protocol. However, it allows for communication that is fundamentally secure and almost imperceptible from the perspective of an external observer. It is impossible to intercept a stream of entangled photons without disturbing it, and this disturbance becomes immediately obvious to the legitimate parties. Now let's apply this concept to interstellar communication. Imagine a civilization far more advanced than ours, mastering quantum entanglement on a cosmic scale, able to establish communication channels between probes and home worlds that are invisible to anyone outside the entangled network. From our perspective, using radio or optical telescopes, we would see nothing. No signals, no transmissions, no evidence of communication. The probe and its controllers could be in constant contact, exchanging vast amounts of information, and we would be completely blind to it. This is not science fiction. The physics is understood, even if engineering for interstellar distances is not yet available. If a probe like the three-eyed Atlas used quantum communication, we wouldn't have been able to detect it unless we intercepted and measured one of the entangled photons. And even then, we couldn't decode the information without knowing the encryption scheme. The canal would be quiet from our perspective, not because nothing is said, but because we are looking with the wrong eyes. High-directed low-voltage laser links are another way of stealth. Instead of broadcasting radio signals in all directions like our early technology due to its simplicity, a more advanced civilization would use narrowly focused lasers to transmit information directly to its target. The beam will be narrow, possibly with micro or even nanodegrees, illuminating only a tiny patch of space. If you are not in that patch, if the rays do not intersect with the Earth at the moment of your observation, you will never detect them. The energy efficiency of such systems is impressive. Wide broadcasting of radio waves results in most of the signal scattering in empty space. It's a meaningless waste. Directing a laser beam, almost all energy is focused exactly where needed, significantly reducing energy requirements. For a probe operating with limited energy, this efficiency may be necessary rather than optional. Therefore, the probe constantly communicates, but only in directions we cannot observe. Beams that completely miss us or are so weak they are lost in the background noise. Dispersed spectrum technologies, borrowed from military communication, offer another way to conceal signals. You take your message and spread it across a very wide range of frequencies so that at any given frequency, it appears as noise. To decode the signal, one must know the scattering pattern, the key that indicates how to assemble the distributed parts. Without this key, complex receivers will only see random fluctuations indistinguishable from thermal noise or cosmic background radiation. The CT project, engaged in the search for extraterrestrial intelligence, traditionally looked for narrowband signals that clearly indicate technological origin, as they are too narrow for natural processes. But if extraterrestrial communications use a scattered spectrum, we might completely miss them. They could be all around us, perceived as noise because we don't know the decoding pattern. It's like trying to understand a language you've never heard. It sounds like meaningless noises until you learn the grammar and vocabulary. Radio and television broadcasts of humanity inefficiently leak into space, which is a byproduct of the imperfection of our technology. We are becoming better, transitioning to fibers and directed transmitters, reducing our electromagnetic footprint. An advanced civilization would have made this transition long ago. They would not allow leaks. They would communicate accurately, efficiently, and unnoticed by outsiders. From their perspective, broadcasting widely would be like shouting their secrets in a crowded room, ineffective and potentially dangerous if there are hostile listeners. Therefore, when we seek signals from the thrice-smart Atlas, we use our methods and assumptions about how communication works. We are searching for radio transmissions, optical flashes, anything we can detect. But if the object uses communication methods beyond our current technology, we might be in conversation and never realize it. The silence we perceive is not the absence of communication. This reflects our own technical and conceptual limitations. It has profound implications for how we interpret the silence around the three-dimensional atlas. Perhaps the agencies are not hiding information. They may simply have nothing to communicate because they are searching with the wrong tools. The object can constantly transmit signals, a beacon visible to anyone with the right receivers, but we do not yet have such receivers. We are like people from the 19th century trying to watch television. Signals exist and fill the air, but without the necessary technology to decode them, you will never know about it. Here is a modest lesson about the limits of knowledge. We tend to assume that if something exists, we can discover it with enough effort. But this assumption is only true if the object cooperates with our detection methods, if it exists in a form we are ready to recognize. Quantum communication, directed lasers, encoding with an extended spectrum. This is neither exotic nor impossible. These are continuations of technologies we already possess, enhanced and optimized by civilizations with greater time and resources. They render traditional CD approaches potentially outdated, searching for signals that advanced civilizations no longer produce. The downside is that it complicates the search, possibly to the point of impossibility. If we cannot detect signals because they use technologies we do not have, how can we find them? The answer may be that we will never find them until we develop these technologies ourselves, or until they decide to make themselves visible by simplifying their communications for less advanced observers. Is the three-dimensional atlas such a choice? A conscious visibility remains an open question. In our final part, we will completely change the perspective. We will explore our own silence, the decisions we make about what to reveal, what to hide, what to emphasize or diminish, because ultimately the silence around the three-dimensional atlas may be less related to the object and more to us, our fears, our institutional structures, our choices on how to deal with the unknown, and understanding this human dimension is essential for grasping the whole story. Part 15. The main conclusion. Our own silence. We have approached this issue already in 15 parts, examining it from all sides: object, observations, agencies, technologies, possibilities. But perhaps the most important question is not about the three-dimensional atlas, but about us. Why do we remain silent? Not about specific agencies or individuals, but about us as a civilization, as a kind trying to understand our place in a cosmos that is much stranger and more complex than our ancestors could have imagined. The silence around the three-dimensional object atlas may ultimately be ours, not the object's. An object exists as such, regardless of whether it is a comet, a probe, or something in between. It does not choose how to manifest itself, based solely on the physical or engineering characteristics that define its observable properties. However, we choose how to observe, interpret, and report what we discover. And these choices are shaped by factors unrelated to the object itself: institutional pressures, financial considerations, career interests, fear of ridicule, fear of panic, strategic calculations that prioritize control over transparency. Let's first discuss ethical questions. What should scientists publish, and what should they keep secret? The traditional answer is everything, provided it is peer-reviewed and verified. Scientific achievements occur through openness, through the exchange of data and methods so that others can replicate, challenge, and deepen knowledge. But this ideal concept faces practical realities. Some discoveries have implications for national security. Some data, if published prematurely, can cause public harm due to misinterpretation or panic. Some data is confidential, collected using tools or methods that must be kept secret for competitive advantage. The tension between openness and these conflicting pressures is not easily resolved. Who decides when an anomaly is safe to reveal? In democratic societies, theoretically, this is decided by the public through elected representatives who control scientific institutions. In practice, decisions are made by non-elected administrators, academics with institutional connections, and foundations that set priorities. The public learns only what passes through these levels, what survives the review process, and what is deemed suitable for general consumption. This is not necessarily sinister, but this is how complex societies function. However, it creates a distance between discovery and revelation, and in this distance, information can be distorted, delayed, or lost. How do national interests, public panic risks, and financial pressures shape the disclosure of information? Immensely. A space agency considering announcing an unusual discovery must calculate the consequences. Will Congress respond with an increased budget for anomaly research or cut funding if the agency appears unreliable? Will the public react constructively, or will conspiracy theories and panic dominate? Will the international partners share additional data, or will they unite and withhold information? These questions have real answers that affect real careers and institutions, influencing behavior in ways that slow or stop the disclosure of information, even when formal suppression is not implied. Let's give similar disputes from the year 2025. Intense debates in genetics were held about when and how to publish data on the risks of hereditary diseases. Publishing too early, before therapies are available, means causing concern without offering solutions. Publishing too late means missing opportunities for early examination of those who could benefit. In the field of artificial intelligence, researchers debate whether to publish certain algorithmic achievements that could be used as weapons or for surveillance. Discussions in climate science continue on how to convey forecasts without downplaying risks or frightening the public. These questions have no simple answers. They are dilemmas on which reasonable people can have differing opinions, and the situation with the three-eye atlases falls into the same category. If observations indicate something truly anomalous that may suggest the presence of intelligence, when and how should this be reported? After all checks are completed, after international consultations, or immediately to ensure global involvement in further observation? Every approach can be argued for, and a mistaken choice can have serious consequences. It is important to note that delays are often structural rather than intentional. Large organizations act slowly. The data must be processed, analyzed, and verified by several parties before it is ready for publication. This takes time, especially in the case of complex or unusual findings that do not fit standard templates. What may seem like external oppression may actually be the ordinary pace of the institution's work. Slow motion, exacerbated by the extraordinary nature of the discovery, occurs because bureaucracies are not designed for speed, but for thoroughness, minimizing errors, and protecting institutional interests. These goals contradict the need for rapid information disclosure and bring us back to the theme of three-eyed atlases. If we assume that silence is evidence, we must be careful not to create a self-fulfilling prophecy. The longer the agencies remain silent, the more suspicious their silence appears, leading people to assume that something is being hidden, which then affects the perception of any subsequent information. If the agencies finally publish data showing that the three-eye atlases are just a comet, skeptics will claim that this is a cover-up and selective disclosure of the truth. If they provide data indicating anomalies, critics will question why it took so long. Silence creates a deadlock in which institutional reputation suffers, regardless of the truth. It is the paradox of conspiracy theories. They cannot be disproven. Evidence against the conspiracy is interpreted as part of the conspiracy, and the absence of evidence is seen as successful suppression. The only way to break this cycle is radical transparency, immediate disclosure of all information, but this comes with its costs and is often impossible due to legal considerations of confidentiality, security, or the need for verification. Thus, institutions find themselves trapped, unable to satisfy skeptics without sacrificing other values they must uphold. It is important to remember that as we move forward, we should question every silence, but do so responsibly. Questions about why agencies withhold information, why data is not shared, why some findings are emphasized while others are silenced, require attention. However, it is important to remember that not every delay is malicious, and not every silence is suppression. Sometimes silence is caution, sometimes uncertainty, and sometimes just the slow workings of institutional mechanisms. To distinguish these situations, one must pay attention to patterns over time, the history of agency work, and whether they disclose information or it only emerges through leaks and pressure. Regarding the 3AI Atlas project, a responsible approach involves staying vigilant, monitoring agency publications, advocating for open data to allow independent researchers access to raw observations, supporting initiatives like the Galileo project aimed at creating parallel transparent observation systems, and demanding accountability when delays seem excessive and explanations insufficient. At the same time, it is important to show a degree of trust, understanding that unclear information indeed creates difficult choices about what to say and when. This broader rule applies not only to one object. We are entering an era where our tools are sensitive enough to detect things we do not understand. Fast radio bursts have emerged from nowhere in the data, challenging our theories. Gravitational waves have opened a new window on cosmic events we could only imagine. The more we observe, the more anomalies we find, and each of them generates the same tensions between information disclosure and caution, between speculation and verification. Our choices on how to handle these tensions will determine what kind of scientific community we will become. Will we embrace transparency, accepting the chaos and uncertainty that come with it? Or will we prioritize control, accepting the suspicions and delays in progress that it creates? There is no perfect answer. Each approach has its drawbacks, but recognizing these drawbacks, discussing them openly, and engaging in debates is essential. The loudest truth may wait in the silence between the stars, but to hear it, one needs not only tools, but also courage. Courage to hear what challenges our beliefs, to accept uncertainty instead of rushing to premature conclusions, to acknowledge our ignorance when we don't know, rather than inventing comforting stories. And faith is needed. Faith that others are also trying to understand. Faith that institutions, although imperfect, act in good faith most of the time. Faith that the truth will ultimately emerge if we continue to ask questions, observe, and demand accountability. The 3AI Atlas project will eventually become too weak to be tracked even by our best tools, but the questions it raised will remain. What are we ready to see? What are we ready to acknowledge? How will we balance caution with curiosity, responsibility with transparency? These questions have no definitive answers. They will arise with each new discovery, every new anomaly, every new visitor from outside our solar system. Therefore, keep an eye on agency messages, stay curious, demand open data, support transparent science, but also show epistemic humility, recognizing the limits of what we know and can learn given current technologies and methods. The universe is not obliged to make itself understandable. It is vast, ancient, strange, operating on scales and principles that challenge our pursuit of mastery. The three eyes of the Atlas are just a tiny thread in this cosmic tapestry, reminding us that we are still at the beginning of our journey to understand this incredible universe we inhabit. Silence will eventually be broken. It always is. Data will accumulate, interpretations will refine, new observations will narrow possibilities. Perhaps we will confirm that this is a comet, unusual yet natural, and move on to the next mystery. Perhaps we will find evidence that truly challenges our understanding, forcing us to expand our conception of the possible. In any case, the process continues. We observe, ask questions, engage in discussions, slowly moving toward understanding. This is a scientific project, convoluted, slow, and imperfect, but still the best method we have for navigating the unknown. In this process, silence is not the enemy. The enemy is the deliberate suppression after silence. But the silence of caution, verification, and time for understanding before speaking has its place. The art lies in knowing the difference and demanding accountability when the wrong type of silence prevails. With the three eyes of the Atlas, this art is still practiced. We are still in the middle of the story, not at its end. How this story concludes depends not only on what the object is, but also on what we decide to do with the gathered information. Therefore, we wait, observe, and ask questions. We demand accountability from our agencies while recognizing their limitations. We advocate for transparency, understanding the complexities that sometimes require caution. We remain open to unusual opportunities, demanding unusual evidence in return. And amidst all this, we remember that the greatest silence we must overcome is not among the stars. It is within us. The silence of unfounded assumptions, suppressed curiosity, lost wonder, replaced by cynicism or complacency. The universe speaks. Whether through the three eyes of the Atlas or 1,000 other signals, it tells us that we are not alone in space and time. We are part of something much grander and stranger than we can imagine. Our task is to listen, truly listen, using all the tools and wisdom we can gather, and to keep listening even when the silence feels overwhelming, even when the answers seem incredibly distant. Because it is in this persistence, in this constant striving to ask questions, that our best hope lies to finally hear what the cosmos has been trying to convey to us all this time.